Okay, so now we're going to talk about the statement of the second derivative test. We'll sort of talk through that a little bit, and then the next after that, then we'll go through some specific examples with some particular functions. So, if the second derivative test says this, if f prime of c is equal to 0, that is to say, c is a type 1 critical value from the first derivative, if f prime of c is equal to 0, and the other requirement is that the second derivative must exist. So f double prime exists in an open interval containing c. In an open interval containing c. So f prime exists in an open interval containing c. Looks like that. How about if I write that legibly? In an open interval containing c. So it's a type 1 critical value from the first derivative. If the second derivative exists on an open interval containing c, all the work that we are going to do this semester, the second derivative will exist for our work. Then, this is the nuts and bolts of the second derivative test. There are three possible scenarios. Number one, if the second derivative evaluated at c is greater than 0, then there is a relative minimum at x equals c. Second scenario, if the second derivative evaluated at c is less than 0, then there is a relative maximum at x equals c. And then the third scenario, well, if you're not greater than, you're not less than, there's one other scenario. That's if the second derivative at c is equal to 0. Then there is no information. Sometimes you'll hear people say the second derivative test has failed. Another way to say that is the second derivative test is non-conclusive. What it means in the third scenario, if the second derivative evaluated at c is equal to 0, it could be there's a relative maximum. It could be there's a relative minimum. It could be it's neither one of those two. And so in the third scenario, there is no information given from the second derivative test. And we'll talk through the details of how that works out. Now, the rationale for this is, it should be fairly straightforward. One thing to bear in mind is, and this is always the case, if you go on to Calculus 3, there will be the three-dimensional version of the second derivative test. Everything we'll do here, you'll do in 3 dimensions. And it is exactly similar to this. Notice how it's opposite. Usually we associate greater than with big, but in this case, greater than means it's a relative minimum. Less than means it's a relative maximum. Now the reason for that is this. Recall that if the second derivative is positive, that means the curve is concave upward, it cups upward. And so the value you have is a relative minimum, right? So it's concave upward. The value you're seeking is the middle. That's the relative minimum value because it's concave upward. On the other hand, if the second derivative is less than 0, Remember, if the second derivative is less than 0, that means the curve is concave downward. And then this point would be a relative maximum point. It's the top point. So if it's greater than 0, that means it's concave upward, and we're talking about the bottom of the bowl, and the bottom of the bowl is the relative minimum. But if the second derivative is less than 0, that means it's concave downward, and now we're talking about the top of the umbrella. That's a relative maximum. If the second derivative is equal to 0, there is no information. It could be that there's a relative maximum. It could be there's a relative minimum. It could be it's neither one. In the third scenario, don't conclude too much. Don't conclude it's neither one. If it's in the third scenario, something else must be done. Typically, if you're in scenario number 3, what that means is you must go back and do a first derivative analysis, at least a part of it. And we'll talk about that as we work through the examples. So that's the statement of the second derivative test. Remember that it is opposite. Greater than means relative minimum, less than means relative maximum, and yes, I am wearing my Kansas City Chiefs World Champion shirt.